Welcome to the Matrix. I mean, physics can be fun with Stephen Thomas. Do you remember how in the movie The Matrix, Neo experienced déjà vu, which meant that the Matrix, that artificial universe, was breaking up? And he experienced it when he saw a black cat twice. I think I'm experiencing the same déjà vu. Excuse me one moment. I've seen this black cat more than once today. It must be a breakup of the universe. Now, the universe has to operate by very precise laws. And just like the Matrix, but it's even more complicated, obviously, than that artificial fiction movie, The Matrix. And in this universe, there are various quantities which are conserved, such as energy. Energy cannot be created or destroyed. Every month, God calls in the energy angel and he says, give me a counting of how much energy there is in the universe. Angel adds it up. Yes, that's the same amount as there was last month. Now, there are other physics quantities that also must tally. And for example, Newton 3 says that all forces must have an equal and opposite force. Newton 3, for every action or force to the left, there must be an equal and opposite force to the right. So the force angel is called in at the end of the month, and he's asked to tally up all the forces in the universe, all the left forces, all the right forces, all the up forces, all the down forces, and they must all add up to 0, because force also cannot be created or destroyed. Newton 3. Likewise, today we're going to look at momentum. Momentum is another quantity where at the end of the month, the momentum angel must come in, and if there is 1 kilogram meter per second extra of momentum, that angel is going to be on the red carpet and it's going to get a tick in his ear. Now, let's suppose that some of us are not convinced that momentum before an explosion is equal to momentum after an explosion. Let's perform an experiment. So, experiment. To prove that P before equals P after. That is our experiment. After an explosion. Our hypothesis. P before will be equal to P after will be equal to 0. Because what we're going to do is we're going to start with the balls 0. We're going to have an explosion, 0 momentum, and we expect the momentum afterwards to be 0 as well. So I'm going to explain to you the method, but I know I'm dealing with momentum. I know balls are going to be going everywhere. I'm going to choose a sign convention. I'm going to say, because most right-handed people think that's right, let's choose right as positive, and us lefties, we're sinister, so that'll be negative. Okay, method. So here's what we're going to do. We're going to take a CD case. It's got a piece of a rubber band around it, and it's got a string here to stop it opening too far. We're going to put it 2 balls on your left, 1 ball on the right. Made a mark on the track there to show where we start. Open the CD case just a touch. Get it in position. Now what I'm going to do is I'm going to allow the explosion to occur and leave it for exactly 1 minute. I'm going to count and 1. And then I'm going to stop all the balls. And 1. Let's do that again. And 1. So, the 1 ball ended up here. The 2 balls, I'm going to take the average being the middle between the balls, ended up there. So, that is our results. In 1 second, the 2 went that, so they went that distance per second. And in 1 second, the 1 ball went that distance per second, so that's its velocity. So, let's give the results. Method we've described, results. The two left balls, velocity was meters per second, and that's 0.13 meters per second. And they went left, obviously. The one right ball went 0.25. The one right ball went, so that is exactly 0.25 meters per second right. And if right is positive, left must be negative. This is going to be a negative value. The one right ball is going to have a positive value. So there's our positive velocity of the one ball. There's our negative velocity of the two left balls. So our discussion. Let's add the two momenta before. Let's have the P left plus the P right equals mass times velocity left plus the mass times velocity right, which is going to be equal to. Now the two left balls are going to be 2 times 0.0459 times 0.13 minus 0.13. That is going to be the momentum to the left, and we're going to have the momentum to the right plus the momentum to the right is going to be equal to 1 times 0.0459 times positive to the right 0.25. And let's just punch that into our calculator and get what the final total momentum is going to be equal to. So, two times 0.0459 times negative 0.13 plus 1 times 0.0459 times positive 0.25 equals, and here's the answer that we get. I'm going to write it here because the space is a little bit limited. We get as our answer negative 4,59 times 10 to the minus 4, which means we're going to move our decimal place 1, 2, 3, 4, and our answer really is 0.0000459, and it's a negative value. Now that, if you want the correct units, is going to be kilogram meters per second, and it's negative left. But really, it's naught. That value is as close as anything to naught. So the momentum before, when the balls were not moving, was naught. The momentum afterwards is naught, virtually naught, and therefore momentum was conserved in our explosion. Now I'd like to just quickly demonstrate how momentum is conserved in a collision. Let us suppose that we have one ball stationary and another ball moving to our right. It has a certain amount of momentum. So this one has no velocity, therefore no momentum, and we start with momentum to the right. Watch. Did you see what happened? We started with only momentum to the right. As the one ball hit, the other ball went shooting off to the right, and the first ball that had momentum stopped. So let's just show you that again. So what you saw happen was this ball that had momentum transferred its momentum to that ball. This ball stopped. So the total momentum still ended up more or less the same as it started with, to the right. Let's do that again. So there we see momentum to the right is conserved to the right. Now, maybe that doesn't convince anybody yet. So let's try this. Let's try momentum in both directions to start off with, and my hypothesis is there'll be equal momentum in both directions afterwards. Watch. Did you see that? The momentum before was in both directions, this one coming this way, this one coming the other way, but afterwards, just the momentum, this ball was transferred and it went in there, and this ball's momentum was transferred to this ball, but there was still momentum left and right. Watch again. The momentum before and afterwards is conserved. Now let's suppose you're still not convinced that momentum is conserved in a collision or explosion. Let's take an explosion. We're going to have an explosion such as the following. Again, a seated case with a rubber band to pull it open, and that is going to give a force on both balls. The only question that I have to ask you is, will both balls be pushed? Will they be pushed equally? And will they be pushed for the same length of time? Watch. And the answer is yes. According to Newton's third law, for every push to the right, there is a push to the left. And that is why all forces cancel each other out, or they add up to zero. Newton's third law, for every action to the left, there's an equal and opposite reaction or reactionary force to the right. So both balls are pushed with the same force, and obviously they're in contact with the spring for the same time, so the time is the same, so their force and their time is the same, except the one is to the left, the one is to the right. How can we use this information? Well, we have a formula as follows. We have a formula: force net is equal to change of momentum over change of time. Or change of momentum is equal to cross multiplying force net times time, or delta T. And this concept is so important, it's even given a name, impulse. Force times time, the change of time, is impulse, and that is what changes momentum. The force pushing for a period of time changes the momentum of each ball separately. So the force times the time of the one ball was equal to the force times time of the other ball, if the only difference was the one was left, the other right. So the momentum to the left being negative cancelled out because it was equal to the momentum to the right, which was positive. So the force time to the left, or change of momentum, is equal to the force time to the right, or change of momentum, and therefore, because the signs are different, we add the two momenta together, plus that, plus x minus x, 0. The total momentum afterwards has to be 0.